vectors, unit vectors and vector components, and then vector multiplication, the dot product and the cross product. And vectors are just a means of analyzing a situation. It's sort of a form of mathematics that allows you to come up with the correct answers to problems with less work than otherwise. So some of the notation here is good to start with. The unit vector notation and what they are. Unit vectors have a length of 1. They have a length of 1 and no dimensions to them, not meters, not seconds, and so forth. They have a 1. They're going to be multiplied, and because they have a magnitude of 1, they will not change the value of what they're multiplied on. There are 3 unit vectors because we live in a 3-dimensional space, not counting time as the 4th dimension. But x, y, and z axes. In the x direction, we have the I unit vector. In the y direction, the j unit vector. And the k unit vector is the direction of the z axis. These are not full-fledged vectors. They don't have an arrow across the symbol, just a hat. That's a reminder they're unit vectors. So I made an attempt to make a 3-dimensional drawing of x, y, and z coordinates. So if you use your imagination, turn your imagination on, the x and y are in the plane of the paper. X and y are in the plane of the paper. And the z-axis is coming up towards the camera. The z-axis is coming up towards the camera. These 3 axes are perpendicular to each other. X is perpendicular to y. Z is perpendicular to both x and y. So I hat starts at the origin, goes along the positive x direction. J hat starts at the origin, goes along the y direction, and k hat along the z direction. When we want to describe a vector, we can describe it in 2 ways. We could give the length and the angle, but let's practice with this unit vector notation. So I have a vector A. It's 3i plus 5j minus 2k. That tells someone that the vector has an x component of 3. It's the number in front of the I. It has a y component of 5 and has a z component of minus 2. So I'm not going to attempt to sketch here, but we go 3 units out this way, 5 units in the j direction, and then down into the paper 2 units. And then we would draw from the origin to where that trail left off. So that's unit vector and the vector notation. Now, vector multiplication. There are 2 types of vector multiplication, the scalar product or the dot product, and the cross product or the vector product. So we'll do the dot product first. It's a little easier of the 2. In the dot product, we're going to multiply 2 vectors together, and we will not get a vector result. We'll get a scalar. We'll get something that does not have direction. This will be useful in calculating work. Work is force times distance in a vector calculation. And if we're going to do the dot product multiplication as A times B equals the magnitude of A times the magnitude of B, then we have to include cosine of the angle between the 2 vectors. Cosine of the angle in between the 2 vectors. Otherwise, if we have the components, we can calculate the dot product by multiplying the x components together, multiplying the y components together, multiplying the z components together, and add those 3 terms. So there are 2 methods for finding the dot product. One uses the full magnitude of vector A and vector B multiplied together, cosine of the angle between them. You will get the identical result if you use the second method of multiplying the components together. So let's see how that works. Let's say we have A and B in the xy plane, so the AZ and the BZ are 0. A little simpler example. And we're going to let vector A have a length of 7 meters and 20 degrees to the x-axis. B is 4 meters long and has an angle of 75 degrees to the x-axis. The standard for 0 degrees is the positive x-axis. So compute the dot product. Well, if I lay out the components here in a triangle, so here's our x-axis down along here, and we have some theta, and this works for A and B, but I just wanted to remind you of a right triangle. When we want to know the side adjacent to the angle, we use the cosine function to get that component, the hypotenuse times the cosine of theta. When we want to know the side that's opposite to the angle, then we use A times the sine of theta. So I've done that calculation here for AX, AY, BX, BY. You should check some of those on your calculator. Perhaps pause the video and see if you get the same result. And if I use the first method, A dot B, the magnitude of A was 7, the magnitude of B was 4. Those are the numbers given to us. We had 75 degrees to the B vector, 20 degrees to the A vector. Both of those measured from the positive x-axis. So subtract those two. There's 55 degrees between the two vectors. I do not use 20. I do not use 75 in here. The angle is the angle in between the two vectors. So 7 times 4 is 28 times cosine of 55. Check that on your calculator. 16.1. This was 7 meters. This was 4 meters. So I get meters squared for the units. If I use the component method, here I have the components. So 6.58, the bx is 1.04. 2.39 for a sub y, 3.86 for b sub y. Multiply here, add those two results. You should practice that. And you get 16.1 meters squared. So dot product, we multiply two vectors, we get a scalar result. We do not get a vector for the result. So cross product, a little bit more complicated. Excuse me, used for things such as torque. Again, there are two definitions for the cross product. One of them, if we're going to calculate the cross product using magnitude of A times magnitude of B, then we multiply by sine of theta. This differs from the dot product. It was cosine theta there. It differs in another way. The cross product returns a vector, returns a direction, and will determine the direction, not mathematically, but with something called the right-hand rule. And I'll try to demonstrate this, but you're going to extend your fingers of your right hand, first in the direction of A. It's the first vector. So our fingers extend this way. Then you rotate your wrist such that your palm points in the direction of B, and you can easily bend your fingers in the direction of B. Your thumb will give you the direction of the resulting vector. So right-hand rule, 3 steps. Fingers of your right hand go in the direction of the first vector. You rotate your hand so your palm faces the direction of the second vector, and you can bend your fingers easily into the direction of the second vector. Then your thumb gives you the direction of the result. So I'm using the same two vectors in the example down below, but first the second definition. The next way, mathematically way, to find the result for A cross B, set up a determinant, 3 rows and 3 columns. On the first row, always I, j, and k, the unit vectors. On the second row, the components of the first vector. On the last row, the components of the second vector. So again, using the same vectors we use for the dot product. So I've already worked those out. Using the first method, 7, 4, sine of 55 degrees, 22.9 meters squared. And that's our magnitude, and the magnitude of the cross product is usually different than the magnitude of the dot product, but we have that result. And now if I get my coordinate system back here, A was 20 degrees off of the x-axis, B was 75 degrees, but they're both in the xy plane. So I would put my fingers in the direction of A, then rotate my palm, so my palm is now facing this 75 degrees away from the x-axis, and I can bend my fingers in the direction of B, and my thumb is pointed up towards the camera. So fingers in the direction of the first vector, rotate my wrist around so my palm faces in the direction of the second vector, and I can easily bend my fingers in the direction of B, and my thumb perpendicular to those fingers shows the direction of the vector. So it's in the z direction. That's a k unit vector. It's a k unit vector. So I have 22.9 in the k direction. That's from the right-hand rule. Now, evaluating the determinant that's here, the second way to do the cross product is to write ijk unit vectors on the top row, the components of A, then the components of B. These are the components that were calculated in just a few minutes ago in the video. The A times cosine of 20 degrees gives A sub x, and A sub y, the 7, the length of A, and sine of 20 degrees, and so forth for bx and by. In evaluating this determinant, this works for something 3 by 3, but don't try this rule on 4 by 4 or larger. It also works on 2 by 2. But there are 3 positive diagonals. So first, every time you're going to have 3 factors multiplied together. So I, 2.39, and 0. That's a positive diagonal. J times 0, and then I need a third factor, 1.04. That's a positive diagonal. K, 3.86 and 6.58. That's a positive diagonal. Then there are 3 negative diagonals. So I put in a minus sign, and then I just proceed here. The I needs 2 more factors, so it's coming down this way, 0 and 3.86. The J needs 2 more factors. So there's a 6.58 and the J and the 0. So that's here. And the K, right along here, there's the K unit vector and 1.04 and 2.39. And again, we're working in the negative direction here most recently. So I just insert negative signs. There aren't negative signs in the numbers here, but the 3 positive diagonals that run down and to the right, those are positive. The diagonals that run up and to the right, those are assigned a negative in this technique of evaluating the determinant. And you can see only the K component is going to survive. The I's and the J's always have a 0 factor. So when you do that, you get 25.4K from this term. You get minus 2.5K from this term, and that net out to 22.9K. That's the same result we had from the first method to do the cross product. So there you have a little introduction to vectors. We have the I, J, and K unit vectors along each of the 3 coordinate axes. The components can be represented with the numbers in front of I, J, and K. Just bring that back for a second here. So 3i, 5j, and minus 2k. That vector has components of plus 3 for x, plus 5 for y, minus 2 for the z. And then calculating the 2 vector multiplications. I've got the cross product right here, so I'll do that one. The cross product gives a number and a direction. For AB sine theta, you have to then use your right hand to determine the direction. If you use the matrix method, then evaluating this determinant, 3 positive diagonals, 3 negative diagonals, always have 3 factors in each of the multiplications, and you get your result. Or use the magnitude of the first vector, magnitude of the second vector, sine of the angle between them, and use the right hand rule. Then our dot product, that just gives us a scalar result, either AB cosine theta or AX BX plus AY BY plus AZ BZ, and there is no direction. So you'll find that the dot product is used to calculate work, the force vector dotted into the displacement vector, and you'll find that the cross product is used to calculate torque with force times lever arm. But wait till you get to that, practice with those, ask your instructor if you have questions on any of these techniques.